I'm going to talk about something called the RSK, the Robinson-Shenstedt-Knuth correspondence. And I'm going to take it from a slightly different perspective than it's usually taken. But to kind of give you some historical perspective, this correspondence really, you won't see it in this form, but it started out as a bijection between permutations, pretty nice objects, and pairs of what are called standard Young tableaux of the same shape, so nice combinatorial objects. And this was a bijection that's been known for 50, 60 years. And it was through this bijection that the sort of first results in the direction of Schur measure and Schur processes, all of that sort of machinery came through, in particular work of Logan, Shep, Vershik, and Karoff from the 70s on the question of the longest increasing subsequence of a random permutation. So somehow this perspective of this RSK correspondence is a very old one and kind of defined early developments of the study of Schur measure and Schur process. Of course, I gave you meaning to these things without alluding to this at all, but now I'm going to kind of step back and connect our study of Schur processes to this Robinson-Shenstedt-Knuth correspondence. Okay. Now, oftentimes, if you see this in some nice combinatorial description. You bump and you insert and you have all these different kind of algorithmic rules. You're not exactly going to see it in that form in this lecture, but you'll see what I actually think is a slightly nicer and more unified version of this perspective. So let me just kind of set the stage. So again, we had our model of last passage percolation. So we had these weights, these W11 and Wij at different locations. And in general, they were chosen geometric with parameters AI, Bj. So that was the idea. We had these specialization, these parameters on the bottom, and then the B's on the side, and that specified these inhomogeneous weights. And then we looked, and if we look at the collection of last passage times, I called it G, along a downright path, and I'll focus on a path that kind of goes just to the right and just down. So I have height n and then say height width m. I can look at these collections. So G1n, G2n, these are the coordinates, ij. This would be Gmn down to G m1. And if these w's are random, then the last passage times are random. I'll remind you that last passage times had the interpretation as you look at the maximal path, or the maximal sum of weights along all paths that go from the bottom to wherever your location is. So Gmn would be equal to the maximum over all paths that kind of make their way up and eat up w's along the way. Okay, so just to recall the definition. And what we observed from the perspective of these dynamics on Schur processes, these simple Cauchy identity dynamics, is we observed that these were equal in distribution to the first coordinate, so lambda 1, and I'll use a slightly different notation than I had before. So I imagine that I have the first coordinate of lambda, and I put a super ij for a lambda that's corresponding to position ij. So before I had called this lambda 1. But anyway, and then I have the first coordinate of lambda 2n and the first coordinate of lambda mn and so on and so forth. Where these, so if I chose my w's in this special manner, these random variables jointly is equal in distribution to the joint law of the top of this, where this is distributed according to the Schur process with parameters, again, a1 up to am and b1 up to bm. Which, as you recall, was the top of this line ensemble, this picture that I'm not going to bother to actually try to draw. So this is great, except there's a lot more information in the Schur process, right? There's lambda 2, there's lambda 3, there's lambda 4. And the question that I want to pose is, what, if anything, do these lower parts of lambda have to do with last passage percolation? Okay. Is there some interpretation? And so the answer is going to be yes, and the interpretation is going to be afforded by this RSK correspondence. And so what this will really be, and I'll go into more detail, but this is going to be a bijection from the set of these weight matrices, so W, I, I guess I equals 1 to I in 1 to M, and J in 1 to N. So the set of all such things will be in bijection through this RSK correspondence with the collection of full partitions along the path. So lambda 1n up to lambda mn, and then down to lambda m1. Where these, I require the interlacing up and then interlacing in the other direction down. Okay? So this is the condition, right, that you have supported. The Schur process is supported on partitions. Again, these interlace with the empty partition. So this is the support of the Schur process along this path, and the support of the Schur process is in bijection with the support of the weights, the potential weights of this matrix. Okay? So it's obviously there might be many bijections, but I'm going to define the RSK. This will be a particular bijection. It will have a particularly nice property. Maybe one thing to comment, you should check that the dimension of these spaces, is a sort of Euclidean. I guess these are integer valued, but sort of integer lattice is the same, right? So this has dimension m times n. That's the number. And indeed, because of the restriction that the length of this partition is bounded, so the first lambda 1n, can have length at most 1. This can have length at most 2, and so on and so forth. If you compute this, and we'll draw this in just a little while, you see that the dimension of this set is the same. So at least that's good news. Okay? So what is this RSK correspondence? So one way to define it is through what I would call multipath last passage percolation. And in particular, if I want to, so let's say, forget that these are random for the moment, just take that these are some given integers, or they don't even need to be integers, they can be arbitrary reals for that matter. But I now want to give a map from the set of these W's into partitions. And the way that I'll define my partition, so for a general partition Mn, what I do is I define, so for all k, I guess up to, well, I guess, yeah, for all k bigger than or equal to 1, I define the partial sum of lambda m n sub 1 to sub k by taking a version of last passage percolation where now I assume that I am not just looking at one path, but I'm looking at a k-tuple of paths, so pi 1 through pi k, which should be non-intersecting and live in the box, in the sort of m by n box. So I'll draw what exactly I mean by this in a moment. And then the sum is the weight of that multipath, so it's the sum over all ij, which is in the union of these multipaths of wij. So what do I mean? So let's say that I'm looking mn, capital Mn. So last passage percolation, the lambda 1 was defined by taking the maximal path. I guess I've put 1, 1. I guess I put it here in this picture. So I look at the maximal path over all upright paths that end up at position Mn. Okay? And that I can compute, for a given weight matrix, I have a number, and that's what that number is, and that's what I call lambda 1 super Mn. Now, in order to get lambda 2, I actually compute lambda 1 sub 1 plus lambda sub 2, and the way that I compute that is I look over all pairs of disjoint paths that go in this rectangle. So of course, if my weights are non-negative, it makes sense for the path to be kind of as distended as possible, as extended as possible, right? So what that will mean is that they basically will start off, you can draw it either way. They'll need to start off clustered together and end clustered together. And then what they do in between is up to them, as long as they don't overlap. So maybe it looks like this, one of them, and the other one maybe looks like, like this. And so there's no condition with regard to whether they intersect the original first path. So they're just kind of maximizing over pairs of non-intersecting paths. And then if I want to do lambda 3, I actually compute lambda 1, lambda 2 plus lambda 3, and I look at all triples of non-intersecting paths, and so on and so forth. So from this type of object is actually something people have studied in kind of mathematical physics, statistical physics, because you can think of these as these sort of repulsing or repelling random walkers eating up noise through some inhomogeneous environment. And you'd like to understand some properties of this. In any case, so this is a natural model, and the way that bijection works is through this. And so this is defining, this defines lambda mn, and now I need to tell you exactly, so what the RSK correspondence is that I look at my downright path, in this case this all the way right and all the way down, and I look here at my downright path. And so the weight matrix underneath the downright path is, and this is a claim, in bijection through this RSK correspondence to the collection of partitions that I get along that downright path under this correspondence. Okay, is the statement clear? Let me try to write this out maybe a little bit more clearly. So we have our downright path. So I can think of this downright path. Let's check the dimension, as I said before. So lambda 1n has at most one part. And how do you see that from this definition? Well, you see, if I take a rectangle that has just width 1, there's only the possibility of it supporting one path. And that's just a straight up path, right? There's no hope of having two paths because there's no room. And of course, if I have then lambda 2n, so now I'm looking at a kind of a 2 by 2 rectangle where I can kind of go, then you see I can at most fit two disjoint paths in there. And so this actually has at most two parts. Now, of course, it could happen that the second part is 0. Maybe I only have, 1, 1, 1, 1, 1, and all the other things are 0. So now there's only one path that has a non-zero weight, right? But in any case, if you continue in this way, what you do is you get up to, let's assume m is bigger than n for the sake of this picture. So you get up to lambda nn, and that will have, by the same argument, the capacity to support n paths. But then what happens is once you go a little bit further than that, so here's the nn case, once you get to m being bigger than n, you still can only support n paths. Just because now you're forced, because of not the horizontal width, but the vertical width. You can't support more than n disjoint paths, because if I try to support n of them, they'll just all go horizontal and eat up all of the weights. Okay? So from this point on, your n plus 1n, you stay in this sort of, with the same bottom boundary, n plus 1. And you do so until you get to lambda mn. So I've kind of marched my way along here. I've been doing this RSK correspondence to get partitions as I move along. And then I actually start to decrease. And I like to draw this now by, when I decrease my vertical coordinate, n minus 1, I'll shift the 1 vector down. and I'll keep the n's, the n minus 1 here, and then all the way down to lambda m1, which can have at most one part. So what I'm really getting is I'm getting this sort of parallelogram worth of integers, right? Each one of these is an integer, and so now you can just check that the dimension, so it's n this direction, m in this direction, and so it has the same dimensionality as I had claimed before. But the theorem is, I'll call this theorem 1, is that this defines, so we have our weight matrix W, and we have this lambda matrix under RSK, and that this defines a bijection. We'll prove that. Okay. Any questions about the statement or the way that I've defined the correspondence or why I'm doing any of this? Yeah?
At this stage, is it clear that the equality law?
No. That will be theorem 3. Okay. Yeah. So that's something I say to motivate, but then we're going to prove that. So, okay. So this was theorem 1. Let me state something that's, I think, is kind of remarkable, which is, so this is a bijection, which obviously means that once I know the push forward of a weight matrix, I know the weight matrix. I can just reverse it. But of course, reversing it might be complicated, and reading off nice information from this, from here, might be kind of computationally difficult. So for instance, what's some nice information? Well, okay, we know some nice information that's very easy to read off. So we know that the last passage time is just read off as the top of this, well, of this parallelogram, right? These are just the LPP times. And these multi-LPP times as well. But what's something else that we might want, and certainly do want from the perspective of kind of questions in statistical and mathematical physics? We might want to know what happens if, rather than starting our path at the 1, 1 location, what if we started the path off at the 3, 1 location? And rather than ending here, what if we ended here? Okay, so, you know, or I want to be able to vary the starting and the ending point simultaneously, and I'd like to be able to read off the joint. Well, I'd like to be able to read off if I start off at some position U and I go to some position V on the top. How do I read off the last passage time between those positions from this array? Now, again, in principle, you can invert this bijection and do it. But if you imagine taking n and m to infinity like we like to do, if it's not a nice way of reading it off, you have absolutely no hope of, for instance, deriving the joint law of the last passage time as the starting and the ending point varies, which is something that's of a great deal of interest. It's something that should converge and does converge to an object called the airy sheet. And so what the second theorem pertains to is, how do you read off these varying starting and ending point from this lambda matrix? So let me free up a little board space. Okay, so here's theorem 2. Okay, so for any, so I'm going to again assume, I think, in this setting that m is bigger than or equal to n. For any k between 1 and n, so I'm going to consider k paths, and starting points u1 up to uk. These are, you know, integer, non-negative integer starting points, and ending points v1 up to vk. And any weight matrix W, so, you know, wij, I and 1 to n, 1 to m, j, and 1 to n. If I look now, so let me draw this. Maybe I draw it now with without. So these are the locations of the weights. Hopefully you can distinguish them from nicks on the board. But so each one of these locations holds a weight, a wij. And I look now at the maximal starting point from positions u1. Let's say k is equal to 2, for example, in this picture, and u2. So maybe u1 is here and u2 is here, and maybe v1 is here and v2 is here. So I look at the maximal path through my weight matrix. So my weight matrix is W. So each one of these has a wij sitting on it. And I look at all collections of non-intersecting lattice paths of the sum of the weight. So when I draw this picture, what I really mean is the maximum over all non-intersecting pairs or k-tuples of paths of the sum of the weights along those paths. Clear? So of course, if I had started u1 and u2 paired together and ended v1 and v2 paired together, that was exactly what came into this definition of RSK. Okay? But I'm not restricting myself to that. So the claim is that, and this is a deterministic statement, this is not anything about probability, is that this is equal, that this is recoverable, this number for any u, v, whatever, from another picture, another last passage percolation problem, which is the following. So I have, again, 4 levels. So 1, 2, and then what do I have a width? 6. So 1, 2. So I'm just drawing the same sort of collection of dots, except I'm cutting out the bottom, this bottom corner. And what I'm doing is I'm going to put at each of these locations, I'm going to put what I called in the notes delta lambda vec. So I call this whole thing the push forward under RSK. So if I have my W, I call RSK of W this lambda vec, which is just this matrix. Okay? And what delta lambda vec is it's the thing that I get by taking the matrix and then shifting it by 1 and taking the difference. So in other words, the weight that I put here, well, I use some sort of normalization where I put zeros outside. So here I just have lambda 1n 1. But here I put lambda 2 at height 1, lambda 1, 2 minus lambda 1 of 1n. So, okay, maybe, again, what I do is I take my matrix, I shift it horizontally to the right, and I subtract that from the original matrix. Okay, so pictorially, delta lambda vec is equal to this thing minus the thing where it's shifted over by 1. So that delta, this dotted thing means I shifted it by 1. Okay. So now, what is the equality? So what I do is I take my same u's, so u1 sat above, so I lift it up until it hits this picture, and then u2 sat here, so it sat at position 3, and I lift it up until it hits this picture, and then I put my v's back exactly where they were. I guess 1, 2, 3, 4. Oh, so v went here. And now I look in this environment, I look at the maximal path from u1, u2 to v1 and v2. And so obviously here, u1 needs to go horizontal. And then there's some freedom for what u2 does. Maybe it could do anything that avoids going through this point v1. And I look again at the maximum over all paths of the weights, where the weights are now this delta lambda. And the claim is that this is just an equality. For any choice of k paths, or for any choice of k and for any k starting and ending points. And so what this means is that actually all of these actually these multi-path arbitrary starting and ending point passage times can be read off very nicely through a variational problem in this push forward under RSK. Now, why might this be useful to us? Well, the next theorem that I'll give you, I'll prove these theorems, don't worry. The next theorem that I'll give you, the final one, of course, is going to say that this thing is distributed according to Schur process if the weight matrix was distributed by these geometric AIBJs. Now, we know that this object in the scaling limit, if we look at the edge of it, the upper edge, I take n and m to infinity, I know that somehow these numbers are converging to this Airy process, this Airy line ensemble. And so this gives hope that the behavior of the sort of varying starting and ending point joint laws of these last passage times can be read off in the limit from a variational problem in the Airy line ensemble. And this ends up being true. Obviously, there's significant work to prove that, but this is really a starting point for that observation. So with that in mind, let me write the final theorem, and then I'll kind of start proving things backwards. So I'll prove the final theorem, and then theorem 2, and then theorem 1, which maybe I'll write here. So theorem 3 is exactly what I just said. So if my weight matrix, my Wij's are themselves random with law AIBJ independent, then the push forward of this measure under RSK is the Schur process. So is this P on this, on the downright path that goes along the boundary, just to mn and then down with parameters a and b on this lambda vector. Okay. Is the statement clear? Okay, so this is putting all these things together, you see that you get quite a lot. And you get actually quite a lot more than we had previously seen out of the structure of this last passage percolation model. So let's prove theorem 3. This is actually not hard. Yeah?
In the multipath LPP, what do you call a path? It can be any arbitrary upright path?
A path, yeah, a path is always upright, lattice.
They don't have to be the same length?
In principle, they don't need to. So for instance, in this picture, you see, depending on where my starting and ending points are, they may or may not be the same length. I think here, this one is length 1 less than this one because of the displacement.
The starting point has to be on the left and the bound boundary.
In the definition of the RSK correspondence, in principle, I could allow my starting and ending points to be arbitrary. I don't need to restrict them to starting on the boundary. But of course, you may as well, because I'm assuming the weights are non-negative, and so you can always gain a little bit more, or at least not lose something, by going all the way to the boundary. And actually, in a little while, the way I'll prove all of these results, except this result, I'll prove that right now, but the way that I'm going to prove this theorem 1 and theorem 2 is by doing something which is called a geometric lift of the model, which is to say that I'll basically move from max plus to plus multiplication algebra. And then when you end up defining the analog of this RSK, you actually do restrict yourself to starting maximally displaced in that case. But we'll get to that. Okay, other questions before I proceed? So let's prove this theorem. And my claim is that this theorem immediately follows from theorem 1 and one other thing, one other property, which is an immediate corollary of the definition. So let me write down this, as I gave this to you as an exercise. Okay, so I'll let you do that. If I look at the size of, so under this RSK correspondence, if I look at, I have my lambda mn, and then I have my lambda m minus 1 n, and then of course I have my lambda m n minus 1. Each one of these partitions, so around like a corner, if I look at the size of lambda mn over lambda m minus 1 n, so this is a skew Young diagram or a skew partition. Of course, it's equal to just the size of this minus the size of that, right? And the claim is that this is equal to the sum over all w's that are in column m, so that have coordinate mj for j equals 1 to n. And similarly, if I look at the skew diagram mn over mn minus 1, that this is equal to the row sums. So I equals 1 to m. This is not a hard thing. I'll tell you why, and then you can check it for yourself. What is the size of lambda mn? Well, the size of lambda mn is the sum of lambda 1 plus lambda 2 plus lambda 3. It's the maximal sum here. And the maximal sum here is achieved by taking as many paths as you can fit. But when you take as many paths as you can fit, you completely saturate your matrix. So the size of lambda mn is equal to the sum of all weights in the m by n matrix of weights. And this is equal to it except for getting one column. And so the difference is just the sum of the weights in that column. And same thing for the row. So not a hard point. But with this and the bijection, you immediately get theorem 3. So let me prove theorem 3 now. I think I'll erase this. Okay, so let's call the push forward for the moment p tilde of lambda. Okay, so right now we don't know that it is the same as the Schur process. Let's just call whatever the push forward is under RSK of this geometric weight matrix, call it p tilde, and let's compute p tilde of lambda. So what is the probability of this vector, of this thing I just erased, of this parallelogram of lambda i's? So by definition, to compute the push forward, I should sum over the weight matrix. So this is the weight matrix. These are non-negative weights in an m by n square. And then I put in the probability distribution of the weights. So I product over ij. I always goes up to m and j to n. ai, bj, these are the normalizations of geometrics. And then geometrics, ai, bj, wij. So this is simply the probability of seeing w as my weight matrix. And I sum over all such things. And now I'm computing the probability that my push forward is lambda. And so I'm going to write indicator function that I've done nothing, that RSK of this weight matrix is equal to lambda. Okay. You with me? Nothing hard. But you see, so this factorizes very nicely, right? These are multiplicative terms. So I can write the exact same thing. Okay, let me keep this bit the same. So this all comes down. And I'm going to just rewrite this as the product I equals 1 to m of ai. So you see, ai comes up for every wij as j varies. So I can write this as ai to the sum of the wij's for j equals 1 to n. Right? This is just keeping track of each term where ai occurred. Well, it comes up for wij for all j. And then similarly, the bj's come up when I sum I equals 1 to m of wij. And I take j now 1 to n, and I bring down this indicator function as before. Nothing. I've done nothing so far. But now I notice, well, these are column sums. Column sums? Yeah. Right? This is the sum over the ith column of the weights. And these are row sums. But I know how to rewrite row sums and column sums in terms of actually the lambda that I get through this push forward. So I ought to just erase this and write this as lambda in over lambda I minus 1 n. And this is the size of that. And this one I rewrite in terms of the thing where I change now lambda m mj. So this is I equals 1. This is j. Yeah, lambda m j over lambda m j minus 1. Okay, so these are just by what it was written over here. These are exactly these row sums and column sums, just rewritten now in terms of my lambda. So RSK omega is equal to lambda. But you see now the summation over W, nothing depends on W anymore except for this expression here. So the only term that depends on W is here. So what I can do is I can actually bring my summation inside. So I'm left with the product Ij, Ai, Bj, and then these products of these A, In over A, I minus 1n, and then the B's, and then the summation over all w's of the indicator function that RSK of w is equal to lambda. There is, for every lambda, one w for which this is true, and in that case I get a 1. So this is, by the bijective property, just equal to 1. And so what I'm left with is the Schur process. This Schur process measure with the A's and the B's. So that proves it. Okay, so that's very easy proof. That was somehow the first type of proof of the relation between things like Schur measure, Schur process, and this last passage percolation model. Any questions on it? To be clear, there's one subtlety, right? I've assumed here that lambda satisfies this interlacing property. But the interlacing property is really forced upon me, because this is what RSK pushes forward onto. So one needs to check that, actually, that this is only a bijection onto these interlacing partitions. Okay, so I already mentioned now that combining what we now proved as Theorem 3 with Theorem 2 can be very useful for the purpose of understanding asymptotic analysis. And so let me now move to the question of how do you prove Theorem 2 and Theorem 1, the fact that there was a bijection. And I'm going to primarily focus on Theorem 2 because it's somehow the most surprising thing, I think. And the way that I'm going to approach this is through a method that goes back to Nomi and Yamada. It wasn't exactly phrased in the way that I'll phrase it, but it's kind of an unconventional route to studying this RSK correspondence. And the idea will be, first of all, to take the geometric lift, so replace the max plus with the plus multiplication. Now, the value of doing that is that it will turn out that the RSK correspondence can be phrased in that context in terms of relations on matrices. It won't be so clear what I mean for the moment, but I'll explain it. And then out of that, these types of identities really just fall in a very immediate way. So let's erase a little. Let me clear this. This, if you've studied any combinatorics, you'll know this RSK correspondence is somehow a very well studied and object that has a lot of structure that they continuously find new properties or new variants of. Okay, so I want to describe what I'll call the geometric RSK correspondence. Now, the term geometric has absolutely nothing to do with geometric random variables. It has to do with this lifting of max plus to plus multiplication. So just forgive the name. Okay. So this will take us a little while. Let's see how we're doing on time. Okay, we have time. So I'm going to start by defining something that's called a geometric Pitman transform. Okay, so I'll give you the geometric version, then I'll just briefly tell you what is the non-geometric version, and it'll seem maybe like something you've seen before, not necessarily in these lectures, but so I'm going to consider some starting value r, which I'll take to be bigger than or equal to 1, and functions f and g that map the integers bigger than or equal to r to the non-negative reals. Okay. And then I'm going to define what are called geometric Pitman transforms. So then these geometric Pitman, named for Jim Pitman, who introduced the zero temperature version, transforms. So there are two types. There's g dot f, and this will still be a function from z bigger than or equal to r to 0 infinity. And then there's f, it looks like a tensor, but it's just a symbol, which will go from r plus 1, so bigger than or equal to r plus 1. So you shift the variable to infinity. And these are defined in the following way. So g dot f as a function assigns for x bigger than or equal to r is defined as taking the original function f of x and then modifying it by multiplying it by this summation m equals r to x of the ratio of gm over f of m minus 1. And the other one, what I'll denote as f cross g, is defined quite similarly, except I put the g of x thing, and what I put here is just the inverse of what was above it. So obviously there's some property that if you multiply these two things, you get f times g. And this is for x bigger than or equal to r plus 1. And with the convention that f of r minus 1, because that shows up in the denominator, is chosen to be equal to 1 as a convention. So how should you think about these things? So first of all, if I replace max by plus by, or if I go the other way around, what these things become is it becomes something like f of x plus the running maximum for x for m from r to x of g of m minus f of m minus 1. So the division becomes subtraction. And this is something, if you kind of go to a continuum version of this, which is to say, you have some process, I don't know, b1 and b2, you would get something like b1 plus max m, less than or equal to x, maybe between r, of b2 minus b1. This is the type of object that comes in when you study things like reflected Brownian motions, or Brownian motions reflected around their maximum, their running maximum. These types of path transformations that are very popular in studying things like Brownian motion, things like Mark Yor had studied. Okay? So this is a positive temperature version or a geometric version of these types of transformations that come up a lot in the study of path transformations of Brownian motion and other types of objects. Okay? So what? so with this notation, I now define something that I'll give a graphical representation for this transformation. So if I have G and I have F and they're of this sort, what I'll do is I'll draw a cross with a box through it. And on the right-hand side, what this means is that the output is G dot F and the bottom output is F cross G. So you should think of this as a map from input functions to output functions. And the output functions, this one becomes a function from R plus 1, and this one, all the other ones are functions starting at R. Okay? So this is the transformation, this geometric Pitman transform. So what? And what does this have to do with RSK or any of the other stuff I've been talking about? So it will take us just a drop longer to get there. You see, the nature of these transformations, these are already kind of have the flavor of this geometric lifting of last passage percolation. Right? Last passage percolation said, I want to look at the max over the sums, and now you want to look at the sum over the sum over all paths of products. And already here you have things like sums and products going on. And so what will turn out is that you can actually formulate the RSK correspondence very nicely, very concisely in terms of these Pitman transforms. And so I'll give you that, that description. Okay, but before that, I need to give you a fundamental property of these Pitman transforms. So this is the matrix formulation of the RSK correspondence. Okay, so for any r bigger than or equal to 1, again, and a function, we'll call it e, from z bigger than or equal to r to 0 infinity, again with the convention that e of r minus 1 is chosen to be equal to 1 by convention. We're going to define a matrix, which is really a transition, which is really a partition function. I'll describe it in a moment. Define a matrix H sub r of E. So it's a matrix that depends on the function E, and it's going to take arguments which are in z bigger than or equal to r squared, and it will return numbers that are between 0 and infinity. And the ith j, so the way that this matrix is defined is with that the ij entry is given by the following partition function. So let me explain, I'll give a drawing and then I'll explain what it means. So for 1, so I do want z bigger than or equal to 1 here. So for 1 up to r minus 1, I just draw straight lines. And starting at r plus 1, and so on and so forth, I draw lines with a cross and with a dot in the middle. Okay, so what in the hell does any of this mean? So, and then I write an E here. So what I now do is I think of associating to every edge. Edges have weight 1. Okay. And the vertices, so this vertex has weight little er, this one has little er plus 1, little er plus 2, so on. The vertices have weights which are given by let's say ek, which is equal to capital E of k over E of k minus 1. So in other words, the numbers that sit here, this is just equal to, so ER by convention is capital ER over ER minus 1, which by this convention was 1, so it's just that. And then ER plus 1 is capital ER plus 1 over ER, and so on and so forth. So these are just ratios of these capital E. So the way that I want you to think of this is that the capital E and all of these capital functions are like products. These are like products of weights. And by taking the ratios, I recover the actual weights that I care about. So it would be like if in the usual RSK correspondence, rather than having a weight matrix of these W's, I actually filled it with running sums along horizontals. So W plus the previous W plus the previous two W's, and so on. So these capital things you should always think of as running products. And by this mapping, I kind of recover the weights by taking ratios of these. So, okay, I still haven't told you exactly what this HR is. This HR is the partition function. So the ijth entry of this matrix is the partition function from starting off at position I on the bottom and ending up at position J. So let's say if I was over here, then, well, the only partition, so the partition function, of course, means the sum over all paths in this graph of the weights of those paths. And the weights are multiplicative. So if I started off at an I which was less than R, there's only one place I could ever go, which is straight up, and that weight has 1. So my matrix, let's write out an example, H1 of E, or, well, okay, let's write it in HR of E as a matrix looks like the following. So it's just 1 until I get to the rth entry. Right? I can only go from I to I until I get to the rth entry, but then at the rth entry, I can go from R to R, or to R plus 1, or to R plus 2, or so on and so forth. And in fact, the transition from, I always forget, I think I is this and J is this, right? So if I'm in the I equals rth row, then I get here ER, and then this is ER times ER plus 1, and then ER times ER plus 1 times ER plus 2, and so on and so forth. These are the entries of my matrix along that horizontal. Okay. But which, of course, by the definition is just the ratio of the capital E at one place divided by the capital E at R. Right? So really what's happening is these running products are just ratios of the overall running product, capital E. Right, because when I go from R to, say, R plus 2, I cross through this point, and this point. So the total weight is 1 multiplied by ER, multiplied by 1, multiplied by ER plus 1, so on. Okay. So when I draw a picture, I always mean the weight matrix, or the partition function that's indexed by the point on the bottom going to the point on the top. So who gives a fuck? Who cares? Well, here's the key identity that makes everything work, which is that for any f and g of this sort, so for f and g from z being equal to r to 0 infinity, I have the following equality. I'll write it in matrix form, and then I'll draw a picture. And you'll see the picture looks a little familiar. So I take my HR matrix. So I create a matrix using the using the G. I create a matrix using the F. And the product of those matrices, which is again a matrix, an infinite matrix, right? Because this just keeps going on and on and on, is equal to HR plus 1 of F cross G times HR of G dot F. So in other words, the Pitman transform and the original functions are related through this matrix equality. So if you feed them in, So what does this really mean pictorially? And this, hopefully, a little light bulb will go off when you see the picture. So what does it mean, first of all, to multiply matrices? If matrices are representing partition functions, the sum over all paths from one plate to another, multiplying matrices is great because it represents a partition function of two concatenated graphs. And so the left-hand side is simply the partition function, simply, I say. Well, let me give the example r equals 1 for this picture. But it's the partition function where I have two graphs. So when r equals 1, I don't have any of this junk going on the left. So just for simplicity, I'm looking at this part. So I'm going to concatenate two things like that. So I started off with my g thing, because that's on the left. So I have my cross with the g. And these are so the weights here are determined by the ratios of g. So I'll just label it on the left with a g. And then I concatenate with the same thing corresponding to the labels of the f. Okay, so remember, I told you that you should think of these f and g's as running products of weights. And in fact, if you do that, then these actually just become the weights. And the partition function, the product of these two matrices, is just giving me, if I go from I to j, it's giving me the sum over all paths of the product of the weights. Right? That's what matrix multiplication means. So it's the sum over all potential paths. So here's an example of one path, but there could be many such paths. And the equality is saying that this partition function for all I and j is equal to, and again here I've taken r equals 1, the partition function where, but now I have r plus 1. So I have h2. So the first one actually starts offset. So I don't have a cross in the first one. And then I have a cross subsequent. I'm using the f cross g Pitman transform for the bottom. And then I concatenate with h1 of g dot f. And so now I insert in my crosses at every place. And what I put in here, again, I've taken my Pitman transforms and I look at the ratios of these weights. Now remember back to theorem 2, I took the difference, this delta of the RSK image. The ratio of these weights will correspond to doing the sort of geometric version of that difference. And now I look at the partition function. So again, I'm going from I to j. So I to j, I don't know, 5, 1, 2, 3, 4, 5, to j. In this graph given with weights determined by the ratios of these things. In particular, if I was equal to 1, then I would be forced to go up here and then over. And so this is the fundamental identity. Proving this is not that hard. And so I'll leave this as an exercise. It's not completely trivial, but you can do it by hand. So you can prove the equivalence of these two things by hand. Now, what do we do with that? And so now we come to almost the punchline, which is how does this identity along with this definition, how does this imply, or how does this give us the RSK, the geometric RSK correspondence, and then how does it prove theorem 2, and then with a little bit of work, theorem 1. So in a sense, I don't need the definitions of geometric Pitman transform anymore. I just need that they satisfy this equality. So in some sense, I never needed them. I just needed them to show that there is some transform that satisfies this equality. And whatever that is going to give me RSK. It does give you a nice way of computing RSK algorithmically, though, without needing to solve these maximization problems. So here's the RSK correspondence, the geometric lifting of it. So I'm going to imagine my running products of weights So for n bigger than or equal to 1, and d1 through dn, I'm going to think of these as running products of weights. So z bigger than or equal to 1 to 0 infinity. So you should really think of, how should you think of these d's? Think of them as I have kind of an infinitely wide rectangle. I'm actually going to label my rectangle 1 on the top and to n on the bottom. This is convenient for the way that I'll draw things. So it's kind of the opposite labeling I spoke about throughout the rest of these lectures. But then I think of the d's as being kind of indexed by points in this direction. So dn sits on the bottom and d1 sits on the top. And you should think of the little d's, d1, I'll call it d1 of 1, d1 of 2. Each of these ratios, so dn of 1, dn of 2, so on and so forth, these are ratios of the d's. These are the things whose product gives me the capital D. Okay, so you should think of each of these little d's as being analogous to the weights in the last passage percolation matrix. So anyway, so given this running products of weights, I define a transform. I'll call it this curly WD 1 through WDN. This is going to correspond to part of the push forward under RSK with WDK is a function from z bigger than or equal to k, this typo in the notes, to 0 infinity. And it's going to be, and these are going to be defined in the following way. So I take my running products of weights, and I just write these as functions along the top of a picture I'm going to draw. And now what I do is I connect these, and I use this cross, this transformation. So I take the Pitman transform of dn and dn minus 1, and I run it through this cross. So now I get these two different transformations of the dn and dn minus 1. And when I do that, what comes out horizontally still has the first coordinate. It's a function from z1, z bigger than or equal to 1. But the thing that comes out below is a function now from z bigger than or equal to 2. Right? I've lost a coordinate in below. And so I continue to do this. So each time I bring one of the original d's down, and I work my way all the way through. And what I get out on the right, I call WD1. So I take all of these kind of consecutive sequential Pitman transforms, and in the end I get a function. And this is, again, a function now from z bigger than or equal to 1 to 0, 1, to 0 infinity. But I still have all of these outputs coming down, and so what I do is I just start to put them together. I sew them together like I'm doing some sort of crocheting. And I continue in this manner, so there's something coming down. And eventually I get WDN all the way on the bottom. And this is a function that starts off at the nth, at coordinate n. And my claim is that this is the RSK correspondence, the mapping from these d's to the WD1 to WDN. And there's a little bit more information that actually, if you want to get the full parallelogram, but this is essentially the content of the RSK correspondence. So let me substantiate that. So the claim is that this is basically the geometric RSK image of the D matrix, or the D functions. And in what sense is that going to be true? This seems complicated, right? Like you're doing all this stuff. But we can use this lemma to rewrite the meaning of these WDs in terms of paths, in terms of partition functions. And so that's what I want to describe. So I'll leave the lemma and erase the definition. So here's a nice and immediate exercise, which is that if I take H1, so this is the matrix formulation of this correspondence that I just drew on that I just described over there. So if I take my functions d1 through dn, these sort of input functions, these running products of weights, and I multiply them together in this form, you see I can use this equality to sequentially flip terms around. So the first thing I'm going to do is I'm going to use it and I'm going to apply it to this pair. So when I apply to this pair, what I get out is I get out a Pitman transform. In fact, I get out the outputs from at this step. And then I can keep kind of, so I get something H2 and then it's something H1 out. And I can keep kind of moving my H1 thing all the way to the right. Now that action is equivalent to this first row. And so what I get out after doing that is all the way to the right, I get H1 of this omega d1. But now I'm left with, actually, when I move this through, everything else gets kind of shifted over by 1 and replaced by an H2. And so now I repeat the process with H2, and that's equivalent to just the calculation of the next row. And so what I get, all in all, is I get the product Hn of this image, WDn, and then Hn minus 1 of WD, or n minus 1, all the way down to H1 of the image sub 1. Now, what does this mean? Well, again, these are products of these partition functions, these very simple partition functions. So these create more complicated, more interesting partition functions. And so let me just draw what that is. Is it clear how I use this lemma and this definition to relate the left-hand side to the right-hand side? So it just is simply through these application. So what is the left-hand side? So if I look at the ij entry of this left-hand side, again, products of lots of matrices or composition of these partition functions, I'm looking at the following picture. So I have, well, it's all ones. So I have, on the bottom, I have dn, and then I keep composing it with dn minus 1, and all the way up to d1. And if I go from ij, what I'm doing, of course, I can, I have the entries here are the ratios of these d's. So think of these d's again as some running product of weights. And so what I get here is that the ij entry is the sum over all paths that go from, level n, the bottom level, position I at level n, up to position j at level 1. I know I've reversed the n. I've reversed somehow the coordinates 1 and n, but just forgive me, of the product of these I don't know, maybe I'll call them dij's along the path pi. So this is exactly this replacement, if I went to max and plus, of last passage percolation. What is the right-hand side? The right-hand side is, again, a partition function. I start off with hn. So hn means that I have, for the first n minus 1 spots, I have these vertical lines, and then I start at position n with these crosses, and then hn minus 1, and of course what I'm plotting here are the wdn, and then these are the wdn minus 1s, and all the way up to wd1. And so the next level I kind of start staggered back by 1, and then the next level one further. Now this might start to look like the theorem 2 picture, if you recall, because it's exactly that. So what I do is I populate this now with the ratios of these WD images, ratio being the geometric analog of taking this difference, this delta lambda operation. And my partition functions, so if I go from I to j, I don't know where j is, somewhere here, you see I'm kind of restricted. I'm forced to go all the way up to level I, and then I can make my way over. So this is theorem 2 in the case where I only have one path for k equals 1. And in the positive temperature, in this max plus case. It's very easy to go from multiplication plus multiplication case. It's very easy to degenerate this to the max plus situation. You can use this sort of like Laplace method. You can say, like, let the dij's be equal to like e to the beta wij. And now I'm going to take beta to infinity, and I'm going to take the logarithm of this summation. And the only term that survives is the maximal term. And so this identity just passes immediately, and this beta goes to infinity limit to the RSK, the usual RSK identity. But this is only the k equals 1. This is for a single path to a single path. And I claimed an identity, well, this is already nice, but I claimed an identity that holds for arbitrary k starting points to arbitrary k ending points. So any ideas on how you get from that identity to the general k identity? And again, the hint is it's wonderful that we're using matrices, or that we have partition functions here. So it's the answer is 3 letters. I mentioned them in a previous lecture, which is LGV, Lingstrom, Gessel, Viennot. So how many people rapidly ran to look up what that is after my previous mention? Okay, nobody. So what this Lingstrom, Gessel, Viennot says, and maybe I'll say it a little bit more clearly here, is that if I want to know the partition function, well, okay, one way of saying what it means is that if I have a matrix whose entries are partition functions of a graph of this sort, so there's a much more general setting, an acyclic weighted graph, some other language, that if I look at the partition function for k starting points to k ending points, in other words, I'm interested in, maybe not starting just at I1, but maybe I call U1 and U2, and I'm going to go to V1 and V2. How do I compute the partition function? Again, by partition function, I mean the sum over all tuples or k tuples of paths that are non-intersecting in this graph of the product of the weights along the graph. Well, this Lingstrom-Gessel-Viennot theorem tells me that I can compute that as the k by k, as the determinant of the k by k minor, where I take the rows corresponding to U1 through UK and the columns V1 through VK. So the partition function for multipaths are always encoded by the partition function for single path, just by taking minor determinants. But if I take a minor determinant of 2 matrices that are equal, the minor determinants are equal. And the minor determinants here, by the same token, give you the partition functions of k tuples of paths here. Do you understand? So immediately from k equals 1, you deduce the equality that if I took U1 and U2, and I'm going to end up at V1 and V2, that the partition functions on the 2 sides are the same, or 3 or 4 or 5. And that was the general statement of theorem 2. So we gained something by going to this matrix, this positive temperature setting. We could use this Lingstrom-Gessel-Viennot theorem, and we could use these matrix formulations and this very nice description in terms of these Pitman transforms. So this proves the theorem, but somehow there's maybe something a little bit unfulfilling still, because I haven't quite told you that I haven't made it clear why is this the analog of RSK. Well, I define this in terms of these complicated things, these Pitman transforms, right? So a priori, what I've done here might have absolutely nothing to do with RSK. But if you look again at our picture here, if I imagine that the U's started clustered together, so U1, U2 up to UK, and my V's end clustered together, the way I defined RSK was I forced my starting points and my ending points to be clustered, and I looked at the longest triple or K non-intersecting paths of the sum, right? So, well, what is the partition function? The positive temperature analog of that. If my U's start clustered, then here my U's start clustered here. You see it forces that the paths go straight up. And once I'm here, and I want to end up at V1, V2, VK, V3, it actually forces that I eat up all of the weights on the top 3 levels, on the top K levels. So it freezes me into this situation. So it tells me that actually the partition function here is really just equal to the product, right? You see I've used all of the weights now on the top here. So the product of the weights along the first row and the second row and the third row is actually given just by WD1, let's say I'm going up to position where VK is equal to N times WD2 N up to WDK of N, that this is, I guess this is the left-hand side, equal to the sum over K non-intersecting paths that go from the bottom left corner to the top right corner of the product of the weights. And in the 0 temperature setting, in this max plus setting, this is exactly the same as saying that I take the partial sums of lambda 1, lambda 2 up to lambda k, and that equal the k path partition, the k path last passage time. So you recover the definition that I gave you from RSK, at least when you degenerate to the 0 temperature, you recover that definition immediately again from this equality. So you see that actually we are working with the lifting of RSK. Is that clear? Again, RSK asked, in order to populate the RSK matrix, we forced that our starting points and ending points were clustered, and we see that the partition functions for clustered points are immediately read off as the entries of these WD functions. And that's RSK. So this, in fact, what we did just prove here was theorem 2. Maybe that wasn't obvious. Let's see how we are on time. Okay, so let me pause for questions. I can still prove theorem 1, but any questions? Yeah.
You mentioned that U1, U2, UK, they can be arbitrary. What if they're not the first consecutive point?
Well, that's the content of theorem 2. It says that so what theorem 2 said was that if I wanted the last passage time from non-consecutive, non-clustered points, what I could do is I could solve a variational problem. I could solve a last passage percolation problem in this delta lambda matrix, in this difference of the lambda matrix from the same starting points but up to this sort of offset. And so that's the content of this. It's saying if they start clustered, then all I'm doing is I'm actually recovering the definition of RSK. I'm actually showing that this WD thing that I defined in some completely different way was RSK. And moreover, I get out of this that it has this nice property that was the content of theorem 2.
So actually theorem 1 is a special case of theorem 2.
Well, theorem 1 will follow from theorem 2, so I haven't done that yet. But theorem 1 will follow from theorem 2. Let me say something about this Pitman transform. So, I gave you a description of RSK in the 0 temperature, in the max plus case, in terms of these longest k-tuples of non-intersecting paths. But that's not actually the original formulation of it. Originally, RSK correspondence was formulated by a notion of kind of insertion and bumping, some very local algorithm that acts on semi-standard Young-Tepelo, that acts on the sort of lambda matrix in a very, you insert in a new weight, and that causes certain things to move around very algorithmically. These Pitman transforms in this picture is somehow a very nice encoding of that algorithm. Now, the fact that you have that algorithm and that it has this interpretation in the clustered version, right? The fact that that bumping and insertion algorithm can be rephrased in terms, or provides this last passage percolation interpretation, not just for one path, but for k paths. That's something that goes by the name of Green's theorem. That's a very old theorem in combinatorics. And so this is really giving you a proof of Green's theorem, but a very simple proof in the case where you start clustered, and then, of course, a generalization of it to these non-clustered starting and ending points. Okay, so let me not, theorem one, I work out the details in the notes. Let me just kind of tell you the content of theorem one, what it means in the context of this positive temperature plus multiplication setting. So you see here D1, so let me imagine that instead of fixing these so here I kind of imagine a situation where my weight matrix just extends arbitrarily to the right. But of course, if I'm only looking at partition functions up to with capital M, I don't need to use these weights. These weights never come in beyond capital M. Okay, well, you can see that, right? The weights are the vertices here, the ratios of the weights here, they never come in. So all of the quantities on the right, they only depend on values up to capital M. So of course I could have cut this off and thought of this as just a statement about a relationship between an M by N matrix of weights and some outputs. But you see there's something a little bit missing, right? Each one of these, I have n of these weight vectors, and each has length m. So here I have m times, okay, I'm using a lowercase n, I guess. Maybe I should use a lowercase m to be consistent. Who cares? This one has length m, but this one has a smaller length. So somehow what I've done is I've actually only, if you recall this lambda matrix, this what I called vec lambda, which was the push forward into RSK, I've only actually constructed these. So this thing is corresponding somehow to the WD1, this row to the WD2, and this one to the WDN. Here again, I'm assuming m is bigger than or equal to n. So the question is actually, so I haven't actually demonstrated a bijection yet. I've just kind of constructed half of, well, maybe more than half of the picture. So what is missing over here is, well, in the zero temperature setting, what was sitting over there was the result of doing RSK, but now as I kind of worked my way down along this far edge. And in terms of dimensionality, this should have dimension n times n over 2, right? It's an n by n triangle. So in fact, what this corresponds to in this picture is that everywhere along the way, each one of these edges has a function associated to it, right? Because I compose these, I get my Pitman transforms out. So each one of these things has some function associated to it. And if I look at the nth coordinate, the nth coordinate of each one of the functions that sits along each one of these edges. So there's n, this is an n by n triangle, and I look at the nth coordinate, so the final coordinate, I'm kind of restricting myself now to functions that go from 1 up to m. Then that mth coordinate actually plays the role of this missing data for this to be a bijection. So there's a claim in order to prove that, which is the following. This is the claim that I put in the notes. And so let me state that, and then I'll leave it to you to follow the proof. So the claim maybe will make somehow clearer what I was just saying. And the proof of it is very simple from the definition or really from the identity that I just erased. So the proof, and I think there's a slight typo in the note, so let me write it carefully. So the statement is that if I have two functions, f prime, that go from, and it shouldn't be from arbitrary z, so let me say from the integers between 2 and m to 0, infinity, and I have g prime that goes from 1 to m to 0, infinity. And I have some number I'll call g m, again a typo in the notes, in 0, infinity. Then there exists a unique function f and g, so without the primes, from 1 to m to infinity, such that the g function agrees at its final value with this g sub m, and f cross g is equal to f prime, and g dot f is equal to g prime. Or pictorially, what I mean is, imagine that instead of knowing these things, I'm given something here, so g prime, I guess, and I'm given f prime. And I'm also told that the last coordinate here is this g sub m. The claim is that knowing this, I can uniquely reconstruct a g and an f such that this is equal to g dot f, and this is equal to f cross g. You see then, well, no, so why was this then a bijection, this thing I just described? If I know my WD, and I know my WDN, WDN minus 1, and I know the last coordinate that was here, then that lets me reconstruct the functions that are, the full functions that are here and here. And then I can complete this, I can continue this reconstruction, knowing this, and the last coordinate here, I can reconstruct the full function. And I can make my way all the way back to up. So all you need to do is this one reconstruction lemma. And proving this is really a cinch. Well, it took me a few hours, but no. It's really quite easy. So that's what's in the notes, and maybe I'll let you guys think about it. So let me conclude. Okay, maybe it was a little complicated. So the idea is that this RSK correspondence historically played a very important role in the development of integral probability. It's not necessarily as central as it used to be, but nevertheless it's quite important. In particular, this identity has taken a very important role in the last few years with the construction of this airy sheet and the directed landscape. The basic premise of this RSK correspondence is that it gives you meaning to, well, the whole Schur process in terms of paths. And so it gives you a very nice way of mapping, bijectively mapping from your weight matrix into some image matrix, and it gives you an interpretation of this in terms of non-intersecting k-tuples of paths. Okay? Now that's a physically interesting object, especially when the environment is random, and we know how to study the asymptotics in the special case of geometric weights because of this nice decoupling that happens to the nature of the geometric weights and this nice equality of row and column sums in terms of the image under RSK. In order to prove these types of results, and also because these things are independently interesting, all of these partition functions relate to the world of directed polymers. If you've ever seen that, there is a story. Let me make a side note. So, we know in the zero temperature, in the max plus setting, that these geometric random variables are special. They have a nice push forward, right? So there's a natural question. is there a distribution on the weights, on these ratios of the D's, that has a nice push forward under RSK? Nice in the sense of you can do something with it, you have nice explicit formulas. And the answer is yes, there is. If the D's, if the little d's, the ratios of these capital D's, are chosen to be inverse gamma random variables, slightly more complicated than geometric, but not very, so the inverse of a gamma random variable. Again, you can have inhomogeneous parameters that depend on the rows and the columns. Then the push forward on this image is described by something that's called a Whittaker process. So Whittaker process, like Schur processes, are described in terms of local Gibbs measures. You can write the same sort of picture, these Gibbs measures, except the difference is, and I'm not going to go into this, but the difference is that when you, in a sense, I already talked about these Gibbs measures in the second lecture. Remember I mentioned these inverse gamma on a strip, and I mentioned that when you do that, the types of Gibbs measures, right, you have these sort of interactions between different rows. I'm kind of hearkening back to your memory from the last lecture, or that I said that you can think of the Schur process as an n-layer Gibbs measure where you have weights on edges that are dotted and solid edges. So instead of having the indicator functions, again, all that changes in the Whittaker case is that indicator functions, say y bigger than or equal to 0, become these e to the minus y softened versions of indicator functions. So the Whittaker measure is exactly the same type of object as the Schur measure. The Whittaker process is exactly the same type of object as the Schur process, except just with a slightly different interaction, which in terms of the line ensemble, in terms of these interacting random walks, you should think of as as independent inverse gamma multiplicative random walks with an interaction that allows them to actually cross each other, but penalizes them in this double exponential sense. And so that allows you to gain access to lots of different limits, including to the KPZ equation or stochastic heat equation, things I'm not going to go in the direction of, and these types of theorems all have nice implications and limits in those settings. So you gain it's not just that you gain something mathematically that somehow calculations are simpler when you go to this positive temperature setting. You have Lingstrom, Gessel, VNO, and you have this nice matrix formulation, but also you gain something probabilistically. You gain access to new models. Okay, so I'll stop here.